individually grades on the yeah. So I got about getting like feedback anytime over full credit points.
I don't know. It's a good question. I should have done like a test with
Okay, let's get started. How's everybody today? Does it ever stop snowing here? Okay, cool. August.
It tends to go till June.
Okay. I like it, it's just surprising.
Yeah, that's good.
Cool. I'm excited. Okay. Let's see. I feel like there are fewer of you now than there were last night that you're watching this on. I don't know. Alright, let's get started.
Oh, lights.
Lights. Every time.
Yep.
Or most times, at least. Better? Can you guys hear me back there? Why not?
You should put on your first slide lights. Every slide.
That's a great point. Alright. Announcements. We're going to have Project Zero grades for you today.
Let's go.
Yeah. That's great. Project 1 submission happened last night. Right? Some jokers. Yeah. You've been under a rock if this is news to you. It's fine. If you did not finish this, though, keep in mind that there is a late day policy for the syllabus. So all hope is not lost. Also, Project 1 was worth 3 times the points that Project 0 was. That trend will continue where Project 0 was worth fewer points. It was also significantly less effort, right? So if you decide not to do a project because of the point values you saw in Project 0, that is the wrong answer. Although I believe the points were available to you on campus. Yes?
Will they be consistent from future projects onward?
It will not necessarily be consistent, but on the order of. Yes?
How many projects do you think there will be?
So I'm currently planning on having a total of 5 projects. So indexed at 0, we would end on project 4. There's a chance that that number becomes fewer if we move slower than I anticipate for the rest of the curriculum. Yes?
So in the Berkeley project, it gave you like extra credit. Is that applicable with your grading, or is that just the Berkeley thing?
That will be applicable
Okay.
if your heuristics perform better than the baseline they were describing. If it's admissible. Admissible. Okay. All right. So project 1 submission was last night. There will be a project 2 not too long from now, but not this week. So, all right. Last time we wrapped up adversarial search, which included minimax, expect-max, alpha beta pruning. This will be the theme, kind of project 2. It will be similarly Pac-Man, and you will start to consider the behavior of the ghosts. So we'll just increase the complexity a little bit, make better and better Pac-Man agents. It'll be a good time. There also will be a homework coming pretty soon on at least some of these topics. Yes?
Are we going to be using the same projects we've been working on and grading on them?
I'm sorry, can you say that again?
Are we going to be using the projects that we worked on for project 1 to work on project 2?
You will start fresh, but feel free to reuse code as you want. But yeah, you'll start from a fresh set of files. Okay, are there any questions from last time?
I had a question about what project 1 was.
Okay, sure.
I
I just wanted to ask if you could, like, if we had some extra time, if we could discuss, like, some of the potential ways that we can improve the heuristic for the even on the dots problem.
Sure. Yeah, let's do that next class.
Okay.
Yeah.
I'd like to know who got the lowest.
I don't think I'm going to tell you that. Pretty sure they're
Is that to say the best heuristic or the worst heuristic? Yes.
What does it even mean? All right, so this time we're going to kind of deviate from the Berkeley curriculum a little bit. And we're going to talk about knowledge representations, propositional logic, first order logic. We're moving toward something that's called classical search, which if you're familiar with kind of AI literature means kind of something special that we'll talk about this time or next time. But kind of the idea is that we're talking now about symbolic AI, which is traditional AI systems, GOF AI, good old-fashioned AI. So this is the symbolic manipulation of symbols and tokens in order to infer knowledge or to decide how to act upon your environment, things like this. So it's kind of tied to the manipulation, the logical manipulation systems. So that's where we're going to go today. And so is good old-fashioned AI or symbolic AI making a comeback? Question mark. Some people think so, including myself. So that's why I want to make sure that we touch on this at least a little bit. I don't think it'll come up in your projects even a little bit, but it's worth knowing about in any modern AI. So, all right. Let's talk about knowledge. So we've had these agents, right? There is a world. They're representing this world with some model, right? So that's kind of what we mean by knowledge. So we've kind of encoded this up until now in these kind of state representations. And how have we represented these states so far? Some collection of information, tuples of values, right? So things like vectors, matrices, this notion of nodes in a graph, right? These kinds of things. And the point is, these are all kind of explicit representations of state. But maybe there's an alternative way to go about this, and so that might be an implicit representation. So can anybody tell me what that might mean? Yes?
Is it more like you've got an agent who has some sort of like field of values, and we modify those values, and then depending upon that state is applied?
Yeah, in a sense. Yeah, so let's say that we have some initial state, and maybe we have some notion of how we can operate on that state, but we're not really representing it explicitly in code. We just represent what we can, right? So which do you think is better? Depends, right? But if you're not explicitly representing states, then there's a lot of tricks you can play with, kind of memory usage, things like this. And there are certain instances where maybe you can't explicitly represent your state, and so this type of thing can be very powerful. Anybody have other thoughts? Or those are kind of my other thoughts. Yes?
Could you say what it means?
So it's, rather than having a full enumerated, the ability to fully enumerate the world state, you have some initial state and then some way to operate on that. Yes?
I imagine like implicit is what you do with robots more than explicit, because you can't expand the state space in the real world. You just have to act on what you know. So I'm sure for like when you don't know all the information, it's probably
Yeah, potentially. That's a good point. So this will become more clear as we move on in the lecture, but kind of keep this in mind. So starting from the beginning, Socrates hypothesized that knowledge is a matter of recollection rather than learning. I don't actually know what that means, so we're going to start from the beginning instead. But honestly, he was very smart, so it must be something very profound. But this notion of classical planning, this knowledge representation, these logical operators, these have been around since the beginning of AI. You might even consider them kind of how AI started. This was the way people were thinking about AI when we started talking about AI. So a classic example is McCarthy's advice taker. And so this has, you're given some knowledge, right? Some facts about the world. You have some notion of logical operators. We would use this hypothesized system to answer questions about the world, right? And so this famously kind of proposed, or many believe it was the first time it was proposed, that this notion of common sense reasoning would be critical to AI systems. So what does it mean to have common sense, right? Anybody want to take a stab at that? Yes.
To have a general, intuitive definition of the kinds of situations and objects that most humans are expected to come into contact with?
Sure. Yeah, I mean, it's just this, well, I think it's hard to define. That's a good example, probably, of what common sense is. Probably not an exhaustive example, but yes.
Perhaps to be able to respond to novel situations using intuition?
Sure. So what is intuition? This is tough, right? I mean, people look at common sense applied to AI systems today. Yes?
Knowledge you need to have without being explicitly told.
Yeah, knowledge that you have without having been explicitly told. That's a good point. Yeah, all of these. I'm not sure there's a good definition. I certainly don't have one for you. But it's kind of a concept. Okay, so also a little bit later, McCarthy and Hayes published a paper, Some Philosophical Problems from the Standpoint of Artificial Intelligence, in which they proposed using a model of the world to answer questions. So questions like, what will happen next in a given situation? Or what will happen if I perform a certain action? But more abstractly, other kinds of questions like, what is 3 plus 3? Or what does he want? He referring to, you have to figure these kinds of things out, right? Can I figure out how to do this, or must I get information from somewhere else or someone else or something else? That's an important question, right? Do I have the tools to even answer this question, or must I go seek them out? Right? So this is still kind of a hobby study topic today, especially this notion of common sense reasoning. Okay, so the idea here is that we're going to represent our knowledge about the world using some representation language. We're going to use this to form something called a knowledge base. And then we're going to have kind of facts that we know about the world and rules that we can apply in order to kind of infer new facts. So we often use this to reason over our knowledge. So asking questions, inferring new knowledge, like I said, this can be heavily dependent on this language, this representation language that you can code in the system. Right? Okay, so that brings us to propositional logic. Who has seen propositional logic? You all should have, right? I think this is probably covered also in your discrete class. Okay, good. The idea here is that we have some representation language and a set of inference rules that we can reason about facts that are either true or false. Right? Okay, so we're going to use propositional logic in order to model the world in this specific way. So we're going to have something called propositions. These are going to be kind of true or false facts about the world. It is raining, it is cloudy, there is an exam today, this kind of thing. And so each of these propositions is either true or false, although we might not know which it is. Right? So we can combine propositions using logical operators to make something that we're going to call sentences. So this is the part that you've seen before, things like not. Right? Not A is the opposite of A. If you're given not A as a fact, then A is necessarily false. Right? So this sentence can either be a fact or it could be a question. Not A? Question mark? That depends on A. We don't know A. Or I can say not A. Right? A is false. A or B. Right? One or both of A or B is true. This is review, right? Okay. What is this? A. Which means A implies B. If A is B, then B is true. What does that not say?
If B is true, then B is true.
That's right.
Each implies the other.
Yes, so this is a bidirectional implication. If, then only if. Right? A, if and only if B. They're either both true or they're both false. Right? So as I mentioned, we have two uses of sentences. We can give them to you as a fact. This sentence is true. And then you have some truth table of each of these operators, right? And you know that you have narrowed down the world into one of these entries in the truth table, right? Or it can be a question, or we can use these to model things, right? Okay, so now we'll define a knowledge base. This is a list of sentences that apply to the world. So for example, I'm asserting these as fact. So it is cold. It's not rainy. It's rainy or it's cloudy. And it's cold if and only if it's not hot. Right? So knowledge base then describes a set of worlds in which these facts and rules are true. What do I mean by a world? Anybody have intuit what I mean by that?
The universe in set theory.
Our problem space?
Yeah, a specific instantiation of this, right? So a model is a formalization of a world. The idea is that we set every variable in the knowledge base to true or false, and this generates a model. So how many possible models are there? Infinite, I guess, in a philosophical sense, or physics sense, depending on your interpretation. Anyway,
This particular one would be 2 to the 4.
right. So if you look at your number of propositions, it would be 2 to that number. Right. In a non-trivially complex world, that might be a lot. Right. Okay, 2 to the n possible models. So then, each sentence that I've asserted here has a truth value in every model. Right? So these first 3, they're true according to this model. Right, but the last one's not. Does that make sense? Okay. So we define this as if sentence A is true in model M, then we say that M satisfies A. Or M is a model of A. Okay. Alright, so our knowledge base specifies a subset of all possible models, the specific subset that satisfy all the sentences that we've described. Right? So every time we get a new piece of information, a new sentence that we know to be true, this narrows down the set of possible models. Right? Pretty basic. Okay, so what do we do with this knowledge base? Well, we'd like to ask it questions, right? So we're given this set of facts. We want to ask a question like, is it hot? And so what we can do is we can infer this, which is the process of deriving new facts from given facts, and the process generally would be, maybe we'll go over it in a second. All right, I'll get to it in a second. But, okay, so inference more formally, sentence A entails sentence B, and we're going to represent that by this symbol here in the upper right. If and only if every model which satisfies A satisfies B, or in every model in which A is true, B is true, and this is not bidirectional.
So is this distinct from a proposition? Or, what is it? The single directional area?
So inference, it is distinct from inference, but it shares a kind of a property, which is that A is more restrictive than B. So every model in which A is true, B is true, but there could be models in which B is true, but A is not. Right? So it's not there. That's what I mean by that. So if A is true, then B must be true. So we could just enumerate all the possible worlds, right, and check them all against our various sentences. Right? But what might be the problem with that, which I kind of alluded to?
2 to the n plus an exponential.
Yeah, it's too big. Right. So what kind of tools did we have in the past for maybe searching over things that were too big?
Cache.
Search is what I'm getting at, but we'll get to that next. But that's kind of where we're going, right? Okay, so we want to be able to infer new facts. So frequently we're given a knowledge base, or we compute a knowledge base based on our given sentences. We want to produce new sentences, right? And this, in some respect, is inferring knowledge about the world given knowledge that we already have, right? And so frequently we want to know whether the knowledge base here is in point. Right? Okay, so there's a whole set of algorithms, many of which are described in the book, that do this search process in order to find the proof of Q using a set of inference rules. And this is kind of the abstraction that a lot of automated theorem provers use. So you should, if you've done the reading, actually, you know about those. If you haven't done the reading, you should do the reading. But I'm not going to go over these algorithms today. But we do want these algorithms to have some desirable properties similar to our search algorithms that we've had in the past. Mainly, we want them to be sound, which means that they're not asserting things to be true that aren't true, right? Otherwise, the whole point of the exercise is lost. And we want them to be complete. We want them to be able to find a proof or a manipulation of our symbols based on our logical rules and our logical tools that demonstrates conclusively that Q is true given the knowledge base. Right? Okay, so we have this, yes.
Sorry, I was gonna ask, so does that mean that optimality is not something that is cared about in terms of logical inference?
Oh, it's cared about for sure, but frequently much more difficult to obtain. Generally optimality, maybe, but certainly computational efficiency matters. So at the end of the day, if you're looking at like proving some theorem, right, you say, I've got this set of facts, this set of axioms, this set of operators. I want to say whether this statement is true. It's more about knowing whether that statement is true and less about knowing what the fewest number of logical operators it is required to assert them. Does that make sense? But you want efficiency in your search because you want it to answer your question while you still care about the answer to your question. Right? Okay. So we have this set of inference rules, right? So you can imagine if we're given some set of facts, we could start applying these as actions, right, in some notion of search, and start inferring new properties. And if we end up with a property that is what we were trying to prove, then we've done our job. Right? Does that make sense? Okay, so you should have seen all of these, but if not, go through them in your book. Okay, but these are kind of the logical operators that we've seen before. So this inference is often written in this form, so that is, if we start with this, A or B, and we know, not B, right? So this is our rule, this is our knowledge, then we can infer this, right? This is an obvious example, but they get much more complex, right? But this is kind of the notation. Okay, so finally arriving at the proof that I promised you a minute ago. It'll be very interesting, I'm sure, but the idea is that we know cold is true, right? Because it has been asserted. We know then that there's a bidirectional implication between true and not hot, right? True if and only if not hot, we know true, right? So not hot is true in this case. Hot is false. So is it hot? It's not. This is the kind of question that we as non-artificial intelligence agents find pretty trivial in a lot of cases, right? But coming up with a representation and a way to actually go about manipulating this kind of knowledge in code is non-trivial. Right? So that's what this kind of thing is the pursuit of. And then, as I mentioned, these kind of systems have been used to prove properties in math and logic that people could not prove. So, very interesting. Seems dry, but it's okay. So then we take some observation, right? And from this we have some knowledge base that's implied by our observation, or by things that we've previously inferred, or by facts that are given to us, or facts that are written down by some expert, or whatever, right? And we have this process of inference, and that gives us new knowledge that we can then add to our understanding of the world, act upon, or potentially manipulate, right? Okay, so as I mentioned, this kind of has seen great use in the past for some pretty interesting problems. So this notion of expert systems was kind of based on this kind of framework. And here's an example in 1965 where this system was used to identify unknown organic molecules. And the idea was that it would eliminate most chemically implausible or chemically impossible hypotheses. And from this, they were able to identify new molecules. Similarly, we had a way to identify bacteria that were causing severe infections. And then this is the 1970s, and here this system was beating out infectious disease experts in this process. So already in the 1970s, we had AI systems, these expert-based, knowledge-based systems, solving problems that people could not solve, or solving them better than people could solve. Right? But there's this major issue called the knowledge bottleneck. So what might be one really important issue with an expert system, and it's kind of implied by the title expert system? Yes?
The expert?
The expert.
The actual knowledge that you put into the system?
Where does it come from?
The expert.
It comes from the expert, right? Which means you have to find an expert. Then you have to convince or pay that expert to write all the things they know now. Right? That might be kind of difficult because they're probably expensive because they're experts, but also they should know a lot. Otherwise, they're an expert in the thing that you don't care about, probably. Right? They also make mistakes when they're writing it down. Right? So there's this notion of this knowledge bottleneck, and that is that it's very difficult to acquire accurate knowledge in this kind of system. But there are people right now paying domain experts to write down the things they know to be true about their field, adding these to these knowledge-based systems, and then operating logically on these. Yes?
What about spaces where you have degrees of truthfulness or like certain reasonable assumptions based on statistics, but like you know that it might fail this much amount of the time?
That's a great question. So right now we've kind of been in this binary world, right? Like true or false. You can start talking about things like fuzzy logic, in which you're kind of operating over these less binary settings. I won't get into it today, but it's a good point as a whole field study.
Or like if you're trying to adjust for things that you can't observe, right? Like things that
Sure.
chaos situations.
Mm-hmm. Yes.
There's also like the problem of knowledge where you assume you know something to be true, but you instead haven't seen an instance of it being false. Like saying that all ravens are black, and then somewhere in Siberia, somewhere way off from where you're ever going to see, there's a white raven.
Yeah, that's a good point. So what does it even mean to be true? How can you demonstrate that it's true? There's all this classical, Bertrand's teapot type things, where does the bird proof fly? This kind of stuff. Not getting into the philosophical side of that, but yeah, it's a good point. What does it even mean to be true? If it's true most of the time, I pretend it's true all the time, and still we operate on the world. Sometimes, maybe, this kind of stuff. So, yeah, it's a very good point. Okay, so that was all review. Have you guys seen first order logic in your curriculum? Okay, so that's what I suspected. This might be the first time that you see this. Okay, so this is a more sophisticated representation of some notion of knowledge, and it allows you to have more sophisticated relationships between things and more sophisticated inference. It is a higher order form of logic, of which there are many. We're only going to talk about the first order logic, at least today. But the idea is that we can now start to have things like variables, well, we already kind of have variables, but functions that operate over variables, objects, relationships that we can describe between objects, things that aren't possible with propositional logic. Okay, so we have objects. These are constants. This is like this apple. We have functions that take an object and return an object. So that would be like color or color of. So we said color of apple, that might return an object red. Right? We have relations. These are different than functions. These take some tuple of objects and they return true or false. Right? So is this object an apple? Or is this object A adjacent to object B? Or is this object the parent of object B? Or the niece of object B? This kind of stuff. Right? So now we're starting to get a little more complicated than we were able to represent in propositional logic. Okay, so we call this first order logic. The idea, so we have these objects, these are things in the world, and they don't have to be physical things. I mentioned we have the object red, right? Things like this. But they're kind of like nouns, and it's a name that references something, and you can have whatever. They're just tokens, right? That we start to define relationships over. So you can have Apple 1 or My Apple 271, or like No Scope 360 Apple or whatever it is, right? You have the internet. You have the notion of ennui, right? This kind of stuff. Okay, so functions. These are operators, as I mentioned, that map objects to a single object. So things like color of, object next to, social security number of, date of birth, spouse, color of, my Apple 271 might be the object red. Right? Okay, so in addition to function, we have something called predicates. First order logic is often called predicate logic. These are important. So the idea is that these are defining relationships between our objects, right? And so they're like a function, as I mentioned, but they're returning true or false. So this relationship holds, or this relationship does not hold, right? So is Apple parent of, bigger than, has a, right? And it can take a set of objects in some ordered list, more precisely, but you're returning whether or not that relationship that you're describing is true or false, right? Okay, so these are like verbs, kind of in our language analogy. Okay, so using these, we can start to build up more complicated sentences using kind of the logical connections, connectives that we saw in propositional logic, right? So this is a thing like, if X is a fruit, then that implies that X is sweet in this representation. I know that they're not sweet, but you see what I'm saying? If X is a food, that implies that X is savory or X is sweet, right? Maybe that's more accurate. We know that Bob is the parent of Alice, and Alice is the parent of Humphrey. Right? So this is an example where we might be able to infer other relationships from this, right? Bob is the grandparent of Humphrey, for instance. That's the kind of thing you can start to circulate. Fruit. If X is a fruit, that implies that X is tasty, or X is a tomato and it's not. I actually like tomatoes. That was something else.
I love tomatoes.
Tomatoes are so good. Anyway. But in these logical connectives, predicates can appear where propositions were appearing before, but functions generally. Right? Because what does it mean to say color of apple implies color of orange, right? Like that doesn't mean anything. So it's an important distinction. Right? Okay. So we're going to have to kind of get a little more complicated in how we talk about models given first order logic, right? So from propositional logic, we had this notion of a model, which is where we set every variable in the knowledge base to be true or false, every combination of this, right? And we had 2 to the n possible models. They look like this, right? That's not going to work anymore. So now it's much more complicated. And in first order logic, our model is going to have to contain a set of objects, a set of functions and values for all the inputs, a set of predicates plus values for all the inputs. So as an example, if we have the objects orange and apple, we have these predicates is red, has vitamin C, we have these functions opposite of, right? Then our model would be much more complicated, and we would have this list of predicates and their arguments and the values returned, right? As well as the functions, the arguments, and the values they return. Does that make sense? Okay. So the knowledge base then now becomes a set of objects, a set of predicates, a set of functions, and now we also are going to have a set of sentences that use those predicates, functions, and objects, and we assert them to be true. Right? So we say, is red, apple is true, right? Has vitamin C, orange, this is true. Right? And now we start to know things about the word. Okay. We also have something else that allows us to express things a little more complicated. Those are called quantifiers. Does anybody seen these?
Like there exists or all.
Exactly. Right. So quantifiers allow us to make generic statements about properties that hold for the entire collection of objects in our knowledge base. It allows us to say things like all fish have fins or all books have pages. There is a textbook about AI. There exists a student that bought that textbook. I hope.
Oh, funny jokes.
Thank you. I appreciate that. It's funnier when you point out how funny this is. The idea here is that there's some variable plus some binding rule for the variable, right? And And so we have existential quantifiers. There exists an object such that this sentence holds, right? There exists some x such that x is the present. This x is kind of a temporary variable, right? It only exists in this clause here. That's the sentence using the variable. Other examples, there exists an x such that x is a person and the name of x is George. There exists an x such that x is a car and it's parked in the spot E23. There exists an x such that x is a course and it has some CS pure exit, right? That's kind of stuff. Is there a 270? There's not in this. Right? You guys just anyway, there wasn't mine there. So, all right. So we also have universal quantifiers. This is the other one in this set of two, where this is a sentence that holds for all objects that we have, right? So for all x, if x has some student number, x must be a person. Right? Is that true? I know in some universities they have like dogs with assistive animals with student ID numbers. It's pretty cool. Anyway, maybe not. So for every x, if x has a student number, it implies that x is a person, right? Okay, so for example, for every x we have, if x is a fruit, that implies that x is tasty. For every x, if x is a bird, x has feathers. For every x, if x is a book, x has an object, right? But you kind of notice that the strength of the assertion in the sentence was different for our there exists a and for alls, right? When I was giving examples for the for alls, it was for all x. If it's a bird, it implies it has feathers, right? If it's a bird, it implies it has feathers is a weaker statement than x is a car and it's parked in each vehicle. You see how that is the case? Right? There's this extra conditional. If it's a bird, then it has feathers. Not x is a bird and x has feathers. That's different, right? Okay, so we'll touch on that more in a second here. But the idea is that we have these compound quantifiers. So we can say for all x, there exists a y such that x is a person that implies that y is the name of that person. Right? So you have these more complicated relationships. This allows us to get a little more into it. So this kind of intuitively says that every person has a name. Okay, so what are some common pitfalls? I kind of described this here a minute ago, but if you were to say for all x, x is a bird and x is feathered, what does this mean?
Everything is a feathered bird.
Everything is a feathered bird. It's probably not true, but this is a common mistake that people make. This notion of x is a bird and x is feathered kind of seems like if x is a bird, then it is feathered, but those are different, right? And so generally you will see this and being applied to our for all and implication being applied to the state. Sorry, the opposite of that. Implication is generally the right answer when you're talking about all of the things in your set, right? Because there's this extra conditional on the implication. So, for instance, if we say there exists an x, if x is a car, that implies it's parked in spot E23. This is wrong as well. But it's a little more complicated to describe why it's wrong. Does anybody see it? Yes.
This describes that anything that it is a car, they are all parked at E23.
Not exactly. You're kind of getting along the right lines, though. Yes.
You don't have to be a car to be parked in that space, but
Well, that's true of implication, right? Because the implication is not going in both directions. But this is a little more complicated. Basically, the idea is that an implication is true if both the premise and conclusion are true. But an implication is also true if the premise is false. There's kind of a special quality about implication, right? So if there are no cars,
Then someone can
this is true, which doesn't make any sense, right? Anyway, the idea is just kind of to be careful about what logical operators you're applying given.
Okay, so that's to say that this is true if X is not a clause.
This would be true if there is no X that is a clause.
Yeah.
Which doesn't make sense, right?
It doesn't.
Yeah. Okay, so let's take a 5-minute break, and then we're going to kind of try to come up with some examples of this kind of thing together. Does that sound good? Oh, look at that time.
How many times have you practiced this? And this was the half one.
No, it's 1.5.
Oh, okay. No, like this is.
It took 12 seconds to explore 2,000. So it wasn't like terrible. It was still technically faster than the one that I had that extra. That's why I also care about the time aspect. It's like, it might take some minute. Oh, yeah. Yeah. I tried it on medium days. It took over 10 minutes to determine that it was to crash. It's because there's so many
The next one, that's just, it doesn't apply. This is a sentence. This entire statement. And this statement is true always. If this is true, this is true. And it implies this. It's also true. It's just the way that it is.
So, when do you use this?
So we have some, we're trying to evaluate whether set of hypotheses are true in the world. So we start applying these rules, generate queries, so we might say, this is something that is good. We generate this as a hypothesis, and we say, it's true. But where should we get this? The implication itself. Just wait. Yeah, it's kind of nuanced. Yes. Okay. So why don't we start with some objects? Who has an example of an object?
Rock.
Rock. How about someone? I'm sorry? Googly eyes? E-Y? Why?
I think it's just why.
Yes.
Desk.
Dusk?
Chicken nuggets.
Nuggets.
Cosmic horror.
Cosmic horror. I like that, yeah. Okay, so how about some functions? Who wants to define a function over one of these that returns either another one of those or another object? Yes.
Has googly eyes.
As
Is that a predicate or?
it's a predicate, yeah. You see why it's a predicate?
Oh, yeah.
That's okay. Let's try to get a function that will do some predicates too, but yeah.
Is edible?
Also a predicate.
Oh, not a function, sorry. That is a predicate.
I like it. Yes.
Combine.
Combine. What do you mean?
Takes two objects,
That makes sense.
turns a different object.
That will be extremely relevant next lecture when we start talking about action. When I bring in the googly eyes and the cosmic horror and we combine the two. But we're jumping ahead a little bit because now you're talking about kind of manipulating the world based on a set of actions. And that's definitely where we're going with this. But first we need to know things about those. Yes.
Color.
Color. Cool.
Genre.
Genre. So, yes,
Nugget shape.
nugget shape.
We're all hungry.
So this means we might need some more objects, right?
None of these make sense together.
They don't, but maybe they will eventually.
If a rock is blue,
Story we're about to tell.
if a rock is blue, it is not a nugget.
All right, so hold on. So if we say color rock, this evaluates to blue. Right, so blue implies not nugget. Color rock gives us blue, right?
Therefore, a rock is not a nugget.
It implies that
Oh,
it's
it's
not.
implied, so
only if
It's
it's
implied. It could be a nugget, you just don't
Oh,
know.
it could be a nugget.
If it's a pink rock, it could be nugget.
All the rocks, but it could be a gold nugget.
It could be a gold nugget. Yeah.
It's not
You
nugget,
could say,
it doesn't
so
imply
like,
it.
takes in two things and then one of these is a nugget.
So like equality?
Huh?
Equality, is that what you're saying?
Either equality or like, subclass of stuff.
Those would be different, I think, probably, right?
So is there a difference, like, if you were to say, like, if rock has googly eyes, then it is cosmic horror?
I would say so, probably, or it's terrifying. This takes two things. Yeah, we're really disjointed here. Yes.
So it's saying that the color blue itself is not a nugget, but that doesn't say anything about stuff that is colored blue. Is that right? What we have so far?
Yeah, so I definitely did that incorrectly. That is exactly what that's saying.
Okay.
So if blue is true, just in general,
It exists.
blue, yes, then nugget is false. So this isn't really what we got. But yes,
So are all of these objects in the domain of these functions?
that's a good question. So can these functions have different domains? I think it depends on the implementation, but yeah, maybe from a what makes sense perspective, not all functions apply to all objects, right? You can have classes, specific domains. So for instance, we had this, for all x, there exists a y, such that if x is a person, then that person has a name, right? That was there a minute ago. So x and y are kind of different variables that have different domains from our set of objects. Yeah. You guys kind of see where we're going here, but it's complicated.
Is, like, color rock equals blue a sentence?
So it is part of it is what color applied to rock returns, right? So in order to have a model, we had to have a set of functions, their inputs and their outputs. So this is the output of that function
Yeah,
applied.
we're really just a function domain, in that sense.
Yeah. Yeah, so you can have restricted domains though, different domains to a different set of functions, but that's a little more complicated than we talked about. Anyway, you can kind of see where we're going, right? But you would imagine writing down a set of things that you have in your world, or that you have observed in your world, a set of logical operators. You start to apply these logical operators to these set of relationships. You start to define rules over relationships. For instance, if A is the parent of B, and B is the parent of C, and you have this new relationship, grandparent of, right, A is grandparent of C, this is like, this kind of stuff. So that's generally where we're going. But just a little more on this, the ground term, more literal. This is an actual object, right, like an instantiation of an object, versus a variable. So if you have only ground terms, you can convert your propositional representations to literals and go from there, right? So if you have just apples and is tasty, then you can convert this. If you know that that's true, you can just convert it to is a tasty apple, right? And this is a way to kind of start to simplify your models. So if we want to get rid of variables, the idea is to instantiate a variable to a literal. And so we can do this with universally quantified things. So for all x, if X is a fruit, that implies X is tasty. We can just write out the combination, right? So if apple's a fruit, that implies apples are tasty. If oranges are fruits, that implies oranges are tasty. If cars are fruits, that implies my car is tasty. If the sky is a fruit, that implies the sky is tasty, right? All of these are true, right? This is kind of pointing to why you have to be careful with inference, right? Or implication. Because if the sky is a fruit implies the sky is tasty, that sentence can be true even though the sky is not a fruit, right? You see what I'm saying? It's kind of a nuanced thing. Anyway, so we can also start to invent names in order to reduce this as well. So we say if there exists an X such that X is a car and it's parked in spot E23, we can just say car C is parked in E23. C is a car and it's parked in E23, right?
So it's an instantiation of the first rule that satisfies.
Yeah, so there exists an X, right, such that this is true. I've named it. That's the X. It's C, right? And so now I can get rid of this. Okay. Does that make sense? Okay, so has anybody heard of PROLOG? It's a programming language that's designed specifically for things like this. And as a fun fact, in my AI class in undergrad, we had a whole project where we had to work in PROLOG and do this. If you thought installing Python 3 was difficult, you should try using PROLOG. But anyway, it's a general purpose AI programming language. It's based on first order logic. And it's been used to great effect to a lot of things, oftentimes in Europe engineering. Fun fact, some parts of Watson, which was IBM's Jeopardy claim robot, were written in PROLOG. Generally, it's used as a component of larger systems. And so that last note is kind of why this type of AI system, this type of planning that we'll get into next time when we start to plan over this, why this is becoming more relevant, right? So historically we had these knowledge-based systems, but then we ran into this problem where it was difficult to write it all down. We weren't solving as many important problems as we wanted to. I say we, but it was the 70s, so that was nice. But you know, we, the field, it was overhyped, it was overfunded, it underproduced. It's kind of was very closely related to this notion of AI winter that I hinted at in the first lecture. But the idea is that people have started to combine kind of model-free learning-based, deep learning, RLs, things like this, based approaches, and this more classical representation of symbolic logic and symbolic AI into these hybrid systems that are performing really, really well in a lot of applications, such as natural language processing as exemplified by Watson. Okay. Questions? Yes?
So, the combination, I can kind of get wrap my head around it, but would it typically result as like you have some represented state space in what we were previously doing over like a search space, and then you have some other propositional logic component that you can input these states in to make things true and propositional, and then work from there to make more inferences? Or is
you could imagine that kind of being the case. You could imagine having a set of actions that changes as a function of what you know to be true, where what you know to be true is being searched over by a system like this, in a more traditional search sense. This kind of stuff. There's a lot of really cool work out there. Take a look at it if you want. But next time, so we've kind of talked about what it means to be true or false in the world, and kind of the ways we have to assert these things and kind of infer new facts, but what if we want to change what's true in the world, or change our environment in order to observe more smartly what is true in the world, things like this. So we'll talk about logical planning, what search even means now on this type of abstraction, and go from there. So we're a little faster today than I was expecting, so that's what I had. But are there questions? Did you want to talk about heuristics for Pac-Man? Do you want to go home 15 minutes early? What do you want to do? All right, so first of all, any questions?
I mean, if people can still turn in the homework assignment late, I don't know if we can really do it.
That's a great point. That's a very, very good point. All right, so we're not going to talk about any specific solutions to Pac-Man until after the late solution is in place.
Sorry.
No, it's okay. Yeah, we're in. All right.